Hi everyone, my name is Ilham, and in this video right here, I'm gonna talk to all of you guys about the phone book experiment. Some of you may have heard of it, some of you may have not. So what exactly is the phone book experiment? Judging from the name, it's probably like an experiment that uses a phone book, right? Well, yes and no. The term is actually kind of misleading because you don't really have to use a phone book. All you need are two books. I got them right here. Are two books, and it's way better if you have really thick ones like here. So what you actually do is that you put one page on top of each other until they actually make like one big pile right there, and then you can actually see the magic when it's not magic, it's physics. You can actually see it when you try to pull apart these books. When you try to pull these books apart together, you're actually gonna have a much harder time than you would probably thought. Let me show you how it's done. Right, so as you can see here, I'm putting these pages on top of one another like this in a crisscross pattern, and this is gonna take a while. Boy, there's like 600 pages each here. So in the meantime, while I get this all sorted out, maybe you guys want to know more about friction, what friction really is, and etc. So the other me will tell you how it's all done. So let's talk about friction. Well, I'm pretty sure that most of you have already studied this at school, so I'm not gonna break it all to you guys, but I'm just gonna write the general formula, which is that F is equal to mu times M, and so that's the friction here. A small f is equal to the coefficient of friction times the normal force of an object. So if you see one object right, let's just imagine there's an object right here. If you give that f, there will be a frictional force here of f, which is equal to mu n. Now, mu as the coefficient and n is the normal force. You can see, you will know n when you actually observe the vertical forces in this object. Here, n is the force which counteracts the force of the weight of the object, and g. And so, in this scenario, F is equal to mu and g. Thank you, other me, for that interesting talk about friction. Well, I'm not done here yet. There's still a couple more 100 pages to go. So, how about me tell you guys about the mathematical idea of friction, and maybe explain to us all how, in fact, this experiment is theoretically based on. Go ahead. To pull apart those two books together, then we need to discuss about Newton's first law, which is that to make an acceleration happen, or in this case, to pull those two books apart, then you will need a resultant force bigger than zero, or in this case, at least equal to zero. So, F is equal to the resultant frictional forces, which is basically equal to mu mg n1 plus n2 plus n3 until the nth block. So what you're actually getting here is what you can call an arithmetic series, and you probably have studied this in junior high school. So you can actually turn this into mu mg n over 2 1 plus n. And this is the amount of force you're gonna need to pull those two books apart. Now if you pay attention closely, you can see that here n over 2 times n is n squared over 2. And so the force here is it's not linear to the amount of pages, it's quadratic. And so if there are basically two more pages, if the amount of pages are doubled, the amount of force will be quadrupled. if the amount of pages are 5 times more, then the amount of force needed will be 25 times more. So how about if we talk about those pages that me talked about? So that will be n, which is 600 pages for each book, and so it will be a total of 1,200 pages, right? And so the amount of force needed is proportional to 1,200 squared. Just by looking at this, I'm pretty amazed. Okay, that's really interesting. So can you just tell me what are the numbers really? How much force are we expecting here? Good question, me. I can't say for certain, but given the equation right here, and well, if you look at Google, you'll know that the coefficient of paper is 0.33, coefficient of friction between two pieces of paper with an average mass of one piece, 40 grams, gravitational acceleration, 10 meters per second squared, and you put n as 1,200, you can easily get like, 83,000 newtons. Something like that. That's a lot. We don't live in a perfect world, but if you actually just like, we usually expect an amount of error maximum like 25%, so that's basically 60,000 newtons. And oh my god, 60,000 newtons. That's crazy. Alright, let's see if that's true. So yeah, I've got this all packed up, but this isn't what it's supposed to be like. As you can see, I didn't really make it like an even crisscross between one page and the other. So yeah, it's not gonna be as strong as the theoretical part, but let's see how strong it really is. So this is it, and if we try to pull them apart, and I'm seriously trying here, it really can happen. In fact, it can stand like this one here. This is because of the bad placement that I did, but you can actually see that this is actually really, really strong. I mean, it can resist its own weight. So, what else can it? How much can it actually resist? I think that I'm trying to make this all up, but I'm being serious here, and if you don't believe me, then I just took someone randomly right across the hall, and I'm gonna ask him to do what I just did. So, two books right here. Now, look at the camera and try to pull them apart. Stronger! Stronger! He's trying his best. Pull. Seriously guys, they're doing their best. They're doing their best really, really hard. We're trying to rip this apart, but this just goes to show you the power of friction. For this video, thank you very much for watching. In conclusion, the phone book experiment is a very fun but easy to do experiment. All you have to do is just take two books and give yourself enough time to put those pages stacked up on top of each other, and you're gonna have a ton of fun. Assalamualaikum warahmatullahi wabarakatuh.